Hopefully you have already learned what a mineral is. And after all, we've already started looking at minerals, but I haven't yet defined it for you. The textbook definition of a mineral is a naturally occurring inorganic element or compound that has an orderly internal structure and a characteristic chemical composition, crystal form, and physical properties. And the characteristic chemical composition can have variation, but it is, for the most part, consistent. So, how about thinking about what a mineral is and isn't? Is petroleum a mineral? Think for a moment. Does it qualify as a mineral based on the above definition? It's naturally occurring, but it doesn't have an internal structure because it's fluid. Is coal a mineral? It's also naturally occurring. Again, coal doesn't have, it's not crystalline. It doesn't have that orderly internal structure. Obsidian? Obsidian is glass, and glass doesn't have an internal structure. Amber? That's naturally occurring. Maybe it has an internal structure, but is it inorganic? How about opal? Opal is actually a hydrous form of silica and does have a structure, but it's not crystalline like quartz is. So it doesn't count as a mineral either. Pearl? Is pearl naturally occurring? Yes. Is it inorganic? How about salt? That's naturally occurring. It's inorganic. It has a structure and meets the definition of a mineral. Synthetic diamond? Natural diamond is, but synthetic diamond isn't naturally occurring. How about the bottle of vitamins and minerals you have at home? Those aren't naturally occurring, so they're not minerals. Is granite a mineral? No, because that's a rock, and rocks are comprised of many different minerals. How about ice? Ice actually fits into the definition of a mineral. Or water? It's not a solid, so it's not a mineral. The goal of this class, this Mineralogy and Petrology 1, is to teach you the most common minerals that you'll find as you move forward in your career as an earth scientist. And my focus in here is on the silicate minerals, because if you look at this diagram that shows you what are the most common minerals in Earth's crust, and those are the ones that you're going to encounter, 92% are silicate minerals, and only 8% are non-silicates. So we focus on the silicate minerals in here, and of those, the most common in igneous and metamorphic rocks. And so just to look at this, almost 40% of Earth's crust is comprised of plagioclase, and another 12% of the alkali feldspars. So the crust contains a lot of feldspar. The next two up are quartz and pyroxenes, and that includes old pyroxenes, so ortho and clinopyroxenes. And then to a lesser extent, amphiboles, micas, clays, and some other silicates, and then only 8% non-silicate minerals. The oceanic crust is distinct chemically from the continental crust because it is largely basalt and gabbro, and it contains about half plagioclase and the other half is olivine and pyroxene. And the oceanic crust is resulting from a partial melt, so it's just taking the more readily meltable part of the mantle and extracting that, and the result is basalt. And those are coming up at mid-ocean ridges, like the Atlantic mid-ocean ridge, or mantle plumes, like the chain of islands in Hawaii. And it's forming a relatively thin crust of the ocean floor, 7 to 10 kilometers thick. The continental crust is much thicker and much older. And the continental crust is largely granodiorite. So it's slightly has slightly more of the mafic minerals, those with iron or magnesium in them, than the oceanic than a granite, but is more silica rich and rich in the alkali elements, so potassium, sodium, than the oceanic crust. But if we were just going to generalize, granitic rocks are fairly common and contain about a third quartz, plagioclase, and K feldspar, and to a lesser extent hornblende, biotite, and muscovite. And the continental crust is derived from the magmatism that is taking place at subduction zones and accretion of other continental or volcanic arcs onto the edge of the continents. And that's result in the continental crust is coming from, again, partial melting of the mantle at subduction zones, where we drag oceanic crust and sometimes continental crust down into the mantle. We're dragging fluids with it, and those fluids are driven off during the process of metamorphism in the oceanic crust. And the water enters into this small wedge of mantle above the subducting plate, and it partially melts the mantle, like at the mid-ocean ridges. Those basalt melts that derive from the partial melt of mantle rise up because they're more buoyant and enter into the continental crust and change through different processes that make those melts more felsic or more feldspar and silica rich than the basalts from which they came. The result is, in general, a granodiorite composition for the overall crust, the continental crust. The volcanic equivalent would be andesite, that gets its name from the Andes Mountains in South America. And the mineralogy, again, is mostly in quartz, plagioclase, and to a lesser extent hornblende, biotite, muscovite. Andesite has more of the iron and magnesium minerals, and here I give you a mineralogy for an andesite of plagioclase, hornblende, pyroxene, and maybe some magnetite. And the most felsic of the rocks that come out of subduction zones are rhyolites, or granites, and that mineralogy has more quartz, also plagioclase, but less, more K feldspars, and in the case of volcanic rocks, sanidine is the K feldspar, and to a lesser extent biotite and hornblende. The common igneous minerals are the ones that we've already started to look at, and those include olivine, the pyroxenes, both clinopyroxene and orthopyroxene, amphiboles like hornblende, the micas, biotite and muscovite, feldspars, including the potassium feldspars and plagioclase, and quartz. Feldspathoids are like feldspars, but they are found only in rocks that are silica poor, so don't have enough silica to crystallize feldspar or quartz, and are rarer. And then we have lesser oxide minerals like magnetite, ilmenite, rutile, or sulfides like pyrite, or other minerals that come from crystallization of just trace elements like titanium, zirconium, or phosphorus to give us titanite or sphene, zircon, and apatite. So I've been talking about silicate minerals for the most part, and that's one class of minerals. That's making up 92% of the Earth's crust. The other 8% is comprised of non-silicate minerals, and those include minerals like halite that are part of the halides, oxide minerals, hydroxides, carbonates, borates, sulfates, phosphates. I can go on. There are a lot of different classes of the non-silicate minerals, but they comprise a very small part of the crust. We'll see a few of those, the ones that are most commonly showing up in igneous and metamorphic rocks. And I will leave the less common non-silicate minerals to your ore deposits class, or to said strat. The common metamorphic minerals include the aluminosilicates, the andalusite, kyanite, sillimanite, that are all polymorphs, meaning it's the same composition, but they have different forms. Starolite, garnet, zoisite, cordierite, those are all common minerals that we will look at in class. Other minerals include precipitate minerals, so in evaporative environments that are seen in sediments. And those can include quartz, calcite, magnesite, halite, gypsum, sylvite, and hydrite. And hydrothermal minerals that are more common in ore deposits, like the sulfides pyrite, chalcopyrite, galena, sphalerite, molybdenite, etc. All right, what you learned in this module was the definition of the mineral, that Earth's crust is largely comprised of silicate minerals, and of those 40% plagioclase and almost half feldspar, that continental and oceanic crust have different compositions, and that we're going to focus on the most common igneous and metamorphic minerals and rocks in this class.